Hello, thank you for watching my video, and today I'm going to be talking about Taylor series. Without further ado, let's just get right into it. So one thing that I've always wondered growing up is, how do calculators calculate? And I'm not talking about things like addition or multiplication or just basic things like that, but I'm talking about things like sine, cosine, log, or e to the x, or just really obscure values. Things that they never really gave us a nice formula for. And when I got to my calculus class, I was pretty amazed when I found out the answer. Most programmers use the general idea or something similar to something called Taylor series. And I'm going to explain what exactly that is. Before I can explain, I want you to imagine that you're taking a walk. I'm going to use a number line to just make it easier to show the distance that we've covered. And we're going to start at the point 0. The first step that you're going to take is going to be a length of 1 unit, but here's the thing. Every successive step that you take needs to be half the distance that you've covered in the previous step. So, let's take that first step. Okay? Now let's take the second step. Half of 1 is just a half, so we should be at 1.5. Okay, makes sense. Let's keep going. Now, what do you notice here? As we keep taking half a step of the previous one, we keep taking smaller and smaller and more insignificant steps, but we approach this certain value too. Now, this is the general idea that I'm trying to get at, is the idea that if we add numbers up in the proper order, we can make them equal finite numbers. Now, I know this sounds really silly, but think about it like this. If you had an infinite number of things, it would be almost uncountable. Yet here I'm saying that if you add up an infinite number of things in the proper way, you can make it equal a finite number. And a brilliant mathematician by the name of Brooke Taylor discovered this idea. Now, the thing about our friend here is she's basically at 2. If she continues to take infinite steps, if she ever stops taking steps at any point, she will not be at the value 2. So while she continues this pattern up, she will basically be at 2. Now, if you follow this pattern, you'll find that it's not actually possible to be at a value beyond 2. Now, how exactly do we do it? How do we make numbers add up in such a way that they equal obscure values like e or cosine? And I'm about to show you. I'm going to do it for this function f of x equals e to the x, and I'm going to center it at 0. I'm going to explain what exactly center means in a little bit. All Taylor polynomials, or Taylor series, follow this general formula, which is the nth derivative of the function, and you plug in c into it, times x minus c raised to the nth power, all over n factorial. And the way I like to do this is with a table, and I just kind of like to organize things into nice little columns, just so it's a little bit easier for me to read. We're going to start off with n equals 0, and as you see over here, I've written n equals 0, and we just do that for Taylor polynomials. The 0th derivative of this is just e to the x. We plug in c equals 0 into that. We should just give 1 because anything to the power of 0 is just 1. When we plug in, we have all the terms for this. When we plug in those things, everything simplifies to just 1 for the first term. Now, when n equals 1, 2, 3, you should get some things that look similar to this. The first term is 1, second term is x, then x squared over 2, then x cubed over 3 factorial. In other words, 3 factorial is just 6. It looks like this if I just write it out neatly. And to write this in a way that considers the infinite terms, we're going to use this special symbol over here that's called a sigma. This n equals 0 denotes the point that we are starting at for n. And this top number over here represents the n value that we end at. In this case, we want to consider the infinite terms, so we're going to write an infinity up there. Now, I've given you a whole bunch of information, and you might be wondering, okay, but does it actually work? Like, can we actually calculate real values of e to the x? And let's just look at it. This is what the graph e to the x looks like. This is what g of x equals 1 looks like, the 1 plus x, 1 plus x squared over 2 factorial. And notice how in the beginning it didn't quite look like anything at all, but slowly it's starting to kind of line up with our e to the x graph. Degree 3, 4, 5, 6, 7. And if you look over here, it's looking a lot like e to the x around all these values. But as you see over here, it kind of juts off and doesn't really line up. And this is what the idea of a center is. We could start our polynomial at any point on this x-axis, but for this specific function, we're just going to center it at 0, and if you go back and do the steps, you'll see why it's a little bit harder to center this function anywhere other than 0. So here are some other Taylor polynomials. If you do the steps that I've kind of outlined, you should get something that looks like this. And if you kind of simplify, the polynomials that you get, the summation form looks like this. The cosine one is, negative 1 to the n, x to the 2n over 2n factorial, and then sine looks like that, negative 1 to the x to the 2n plus 1 over 2n plus 1 factorial. And these are both centered at 0. Meaning they are the Maclaurin series. A Maclaurin series is just a Taylor series, except when that function is specifically, or that when that series is specifically centered at 0. Now that I've thrown all these facts at you, let me just show you one last cool thing. Take the function f of x equals e to the ix, and I'm going to say let's find the Taylor polynomial for this, or the Taylor series for this. If you don't remember what I is, I'm just going to keep this over here on the side to kind of jog your memory. Now we know that the Taylor polynomial for e to the x looks like this, so e to the ix, we're just going to multiply every single x term by I. Now look over here, I squared equals negative 1, I cubed equals negative I, and I'm just going to simplify all of these terms up here. I just rewrote everything up here just to kind of make it neater for you. And then we simplify the terms, and we see that some of the i's have disappeared, some things have become negative. And what I'm going to do now is just simply separate all of our odd powers from our even powers. So on this side, I've kind of just written that we have all the infinite terms with an even power, and over here, all the infinite terms with an odd power. And over here, notice how all the odd things have been multiplied by an I. Same thing, I've just rewritten it up here so you can just see a little bit better. And I'm just going to factor it and pull out this I from this right-hand side of the equation. Now recall that the Taylor polynomials of cosine of x and sine of x look like this and this respectively. And what do you notice here? Yeah, that's right. These two parts are in fact the same as the Taylor polynomials of cosine of x and sine of x. And so we can just rewrite this as e to the ix is equal to cosine of x plus I sine of x. If we just let x equals theta, we just rewrite this as e to the I theta equals cosine theta plus I sine theta. And if we just plug in pi, we'll get e to the I pi equals negative 1. And this is called Euler's identity, and it's a really big identity, and many consider it to be one of the most beautiful identities in math. It is definitely one of the cooler identities, and it leads to many more advanced concepts. I do want to encourage you to keep exploring series and just these general topics if you're interested, and thank you for watching.